recording so we can do this. So this is 10.6 first that we're looking at, which is torque. And for these sections, what I'm going to be doing is simply giving you an overview first, okay, just an overview of an idea of what we're doing, and then we'll go through an example or two from each section, provided we have the time to get to that. So 10.6, the first idea is that torque is a function of your force and your distance from the rotating axis. So let's start with our definition. So torque is defined as R times F times sine theta. Now, what I like to think of torque as is this, R perpendicular times F. And we'll see that in a little bit where that comes to play a role. And then later on we're going to use this form of it, which is R times the tangential force. If there's a tangential force applied to a circular object, obviously we're looking at rotations here, so we're going to see a lot of that happening. So we're going to look at scenarios where there's like a pulley that's rotating, and now the pulley has a mass we have to account for, and as a result it has a moment of inertia, and then there'll be like a rope hanging from the pulley. Well, that rope will pull down on the pulley, and in that circumstance we'll end up using this third formula here. In other circumstances, when we know the perpendicular distance that the force is applied at, we'll use this one. And in the third circumstance, when we have an actual angle we're looking at. So I think I'm going to jump right into an example for this. Yeah, let me jump right into an example for this one. So let's go to the next slide. I'm going to open this example here. So I'll let you know which examples I'm using. I'm using them out of the text, so give me a moment. I have them loaded already. Okay, so the first one I wanted to look at is this guy right here. Okay, so we're starting with example 45, and this is from the end of the chapter. You'll see all the examples there. So the body in figure 10.3.9 is pivoted about point O, and two forces act on it as shown. If R1 and R2 are given, if the forces are given, and the angles are given, find the net torque about this pivot point. Now, for a problem like this, what we want to think about is that we do not have perpendicular forces, or forces that are perpendicular to the actual distance, or the lever. And in torque, we talk about lever a lot. So I'm going to make this a little bit smaller and put a little side note over here. And what I want to show you is this. If I had, say, I don't know, let's say it's a hinge or a rod coming from a pivot point, okay, and there's the hinge at the left end. And if I had a force applied like this, then this is where I have a perpendicular. And I would have the distance R, and this is called R perpendicular right there. Now, when I look at these problems, I have to recognize that if this force, though, is at an angle, that symbol is no longer called R perpendicular. It's simply called R. And the reasoning behind that is that R is no longer perpendicular to that blue force shown. So when the force and the R vectors are at a 90-degree angle, we can automatically use R perpendicular times force. But when the force is at another angle that's not 90 degrees, the R value here we have to use, F is here, and then we have the theta. And theta is the angle between R and F. So depending upon the scenario, we have to use one of three formulas. So I'm going to start just by writing this first. Okay, we have again three options. And they're all really the same thing. It's just three different scenarios that you might come upon. So this first example, because the angles are not 90 degrees, we're automatically going to use the first formula. Whenever the angle between R and F is 90 degrees, then we're likely going to use the second or third formula. And we'll see when we'll use one or the other of those two. So for the first example, we're going to start with this first formula. Feel free to chime in with questions, obviously. Okay, so if we're using the first formula here, we have to ask ourselves, obviously, how far away is the actual force being applied? And that's the R value. What is the force? That's the F value. And then what is the angle between the force and the lever arm, or the R value in this case, or the R vector. So I have to recognize that torque can be applied in two ways. We can have clockwise torque. Let's remember this. Oops. This is clockwise. This is clockwise, and that's considered to be a negative torque. and this is counterclockwise. And this is considered to be a positive torque. So those are our general rules when we think about torque. So if it's spinning counterclockwise, it's going to be a positive torque. If it's spinning clockwise, it'll be a negative torque. And we're going to continue with this assumption that this is the directionals that we'll use for the rest of this chapter and the next chapter. So again, clockwise, I think in Donachek's class you said clockwise I despise, meaning clockwise is negative, and counterclockwise is the positive. So for a problem like this, the way I like to approach things is I always look at my pivot point first, and I see my pivot point here in the diagram. And now, when I think about it, if I applied a force like this one to this amorphic looking shape, it looks like a rock, if I apply a force like this, it can only possibly turn it in this direction. Again, F2 pulling down on the right can only pull it or turn it in the clockwise direction. F1, though, would cause it to rotate in the counterclockwise direction. So F1 is going to produce a positive torque, and F2 is going to produce a negative torque in this problem. Again, because F2 makes it go in the direction of the clock, which is considered to be negative here. So when I want to figure out the net torque acting on anything, or like a net force, I have to sum them together. Okay, so I'm adding together torque 1 and torque 2 that are both being applied to this object. Now, we know that we use F or RF. I'll be constant with our formula, or consistent with our formula. RF sine theta and RF sine theta. Now, I like to put the negative and positive sign in at this point. So again, because F2 is causing it to rotate in the clockwise direction, I'm going to make that my negative here. So I'm going to put a negative sign. I'll put it in red so you can see where I'm putting it, right there. Okay, so again, my value in this problem for my torque generated because of F2 is negative. I'm not saying that F2, the force itself, is negative. I'm just saying the torque generated from F2 is what's negative here. Okay, I think we lost Spencer. Spencer, you there? Your video's off. Okay, no problem. Just let me know next time so I know you're not. Thank you. Okay, so we have R1 F1 sine theta 1. So let's take a look at what this is. So R1 is given as 1.3. F1 is given in this problem as 4.2. And the units are meters and newtons, so I don't have to convert anything. And then the angle of theta 1. Now be careful here. The angle for theta 1 is not actually what's given in the diagram. So theta 1 is 75. Now, you guys know, because you're good at math, that the sine of 75 is the same thing as doing the sine of... What is it? Sine of 75 is the same thing as doing the sine of... Yeah, 105? No. 105. So, in this problem, remember that this angle here is really the theta that we're using, but it doesn't matter because it's the sine, right? If it were cosine of 75 or cosine of 105, then it would matter. But because it's the sine value, we're not really concerned. So I could use the 75 that's given in the diagram there, but I'm going to use 105 because I remind myself that the theta is always the angle between R and F. Then I go to the other side of the diagram, and I'll use yellow for that. This angle theta over here is going to be 180 minus 60, or simply 120. Let me write it as theta 2 for now. So then I'm going to have minus the R2 value, which is 2.15, times the F2 value, which is 4.9, times the sine of 120 degrees. So again, I'm using the supplement of the angles that are given in the word problem because I'm really looking at the supplementary angle there. I'm not looking at the angle that's given. But again, it would work either way. So what do we notice? We notice that there's a positive torque, there's a negative torque, and the question becomes which of these two torques is the greater of the two torques. And we'll see based on the sign that we get in the end which one it is. So you can chime in with an answer, but I have it here somewhere. I could find it if you guys don't have the number for me. Question 45. Yes.
Great. Yeah, just wanted to kind of call and also kind of check in to see how you're doing as well with the whole quarantine and kind of how the year is kind of panning out.
No, the only time I'm going to choose one of those other two is when the angle is 90 degrees. Because sine of 90 is... Exactly. So it drops off there. So whenever an angle that's not 90 is between R and F, then the torque generated needs to be calculated by using RF sine theta. Whereas you can use R perpendicular F, or R times the tangent force for a thing pulling on the end of a circle like a pulley, if the angle is 90 degrees. Let me show you the second scenario. So I gave you the first scenario in the top right. Let me put the second one. So let's imagine there's a pulley wheel. Okay, here's the center of the pulley wheel. And let's say that there's a weight hanging off the pulley. If that weight hangs off the pulley, and if I think about it, this is the rotating point X, this is R right here. And the applied force will be acting down like this. And that's the third scenario where we would use that. Is that clear what I'm saying there? So this would be, again, the third scenario, and then the one up here, if we want to go back to what R perpendicular was, we would have to get rid of all of this other stuff, and then this is denoted as R perpendicular. So if the R and the F vectors are ever perpendicular to each other, we could use either the second or the third equation, and they're kind of the same thing when you look at it, okay? So again, top two diagrams for the bottom, top two on the right, up here, correspond to these two right here. And let's see what we get as a result of this then. So we have this value here minus this value. We're going to get a negative quantity, I know that. Negative 3.85. And the interesting part here is that it's Newton times meter. Torque is not resolved into units of joules. It's very misleading because when you think about a force times a distance for work purposes, you say that those are measured in joules. And this is a force, and it is times a distance, but it's not written as joules. Is that clear? Okay, it's not written as joules. Keep that in mind on your test and on your exam. Okay, that's torque in a nutshell, but we're going to then apply, we're then going to look at these two scenarios, right, these two arrangements in a little bit in the next section. So I want to go into section 10.7 so that you guys can see an example with a pulley, because now we can calculate the I value of a pulley from the notes from section 10.5. Yeah? That's a great question. So for these problems, it's in degrees. Yeah, for these problems, it is in degrees. And that's only because the angle was given in degrees. But sometimes the angle can be given in radians, and if you have a problem that has radians and degrees involved, you should try to make your units as consistent as possible in the problem. Where's my calculator? Hold on. I'm just reading it out of an answer key at the back, so let me calculate it then. 1.3 times 4.2 times sine of 105 minus 2.15 times 4.9 times sine of 120. I still got negative 3.85. The negative answer indicates that it will move or rotate clockwise, correct? Okay. No problem. Good questions, guys. Yes, the negative answer indicates that it is moving, let's write that down, clockwise, okay? Clockwise. So again, if you get a positive net torque, it'll move counterclockwise. Let's go on to the next section, and then we're going to continue using torque in the next section, so we'll see another example with torque embedded in section 10.7. Okay, so 10.7 is all about Newton's second law. But when we're talking about Newton's second law, we're talking about Newton's second law for rotation. So let's start by thinking about what we have. So first, if we think about Newton's second law, we know that Newton's second law is F equals ma, and that's Newton's second law linearly. Now, if we have something rotating, and this is, I'm on page, just so you know in your book, I'm on page 279 with this diagram I'm going to use here. Okay, if we have something rotating, so they put an image of a rod, this is a good image here, with a mass at the end here, M, and we have an applied force, and we'll say that this force here, okay, we have some applied force right there, and this is going to cause this object and this bar, or this rod, to rotate in a counterclockwise fashion. So for this problem, what we have to look at and ask ourselves really here is that if we're looking at this force, which is acting tangent to the path, let's see if that makes sense why it's tangent to the path now, and this is like a pulley, right, with the rope hanging off a pulley, what we're going to notice is that we can call this the tangential force, which makes this the tangential acceleration. And then you have to kind of go back to sections 10.1 through 10.4 and remind yourself, okay, what is tangential acceleration exactly, right? We have to ask ourselves, what is tangential acceleration? And tangential acceleration, if you recall, is alpha times r. It's alpha times r. Now, if I multiply both sides of this equation next by r, the left side is going to be ft times r. And by definition from the previous slide, that is torque. So I'm multiplying both sides by r, and this becomes torque right here. And then I've got m alpha r squared, or simply torque equals mr squared alpha. But mr squared, if you recall, is your moment of inertia. So this is Newton's second law for rotating objects. So what I want you guys to recognize is this, and it's actually pretty easy to see the connection. Here, look, right? Force becomes torque in this chapter. The acceleration becomes angular acceleration. The mass here becomes the moment of inertia. So those things all kind of correlate, and we're going to see that correlation again when we get to kinetic energy, when we get to work done as a result of kinetic energy. When we get to power in the next section, we're going to see power as a function of rotation, and it's going to be very similar to the power formula that we had earlier when we were talking about linear motion. So what you need to know from this is not really the derivation, but that last formula that's boxed in. Okay, so that's the formula that we're going to be utilizing in this section. Questions so far? Okay, no questions. I'm going to move on to an example from page 281. So let's take a look at this example here from page 281. Sure. Yeah. Sorry. I think I was calling. Trying to find water. probably today. Is that okay? Yeah, I mean, normally some days I might end about 10 minutes early, but I think I really want to get through the two sections, 10.6 and 10.7. We might not get to 10.8 today, though. I want to do one more example at least, and this one looks like a good one, I think, right? Yeah. Okay, so if you guys want to turn to this page in your text so you can have it written there, you can see it on mine, obviously. I'm going to wait till Londell gets back in a minute. Give, I think, Matt a minute to get back also.
Hey, Ashna, this is Jasmine from Welcome Back to Give me a call. With an awesome opportunity with a company called Triage Consulting. I see that you indicated you were interested.
52 should be from section 10.7. I think it should still be on the same topic of Newton's second law for rotation. I'm just looking in the text to make sure I'm saying that right. Yeah. Yep. We'll probably not get to 10.8 today. I was a bit ambitious to say we get through 10.6 through 10.8 just because these problems take a little bit of time and we haven't gone through too many of them just yet. Okay? All right. Londell's back. Is that Maroney? Yeah, he's there. Okay, cool. All right. So we're going to continue with two more examples. I have one here we'll get through and see if we can get to the last example for today. But as you guys just sat down, I mentioned the others, we'll probably not get to 10.8 today. We'll continue 10.8 in the next class. So let's take a look at this example here. So this is number 52 on page 290, in case you're looking, okay? So we've got a problem that says a cylinder having a mass of 2 kilograms can rotate about its central axis through a point O. Forces are applied as shown. F1, F2, F3, F4. Also, the R value in this problem is given as 5 centimeters, and the big R value is given as 12 centimeters. So we want to find the magnitude and direction of the angular acceleration of the cylinder. So when we think about this, the first thing we have to ask ourselves is, what are we solving for, right? What are we actually looking for in this problem? And the second problem is, what the heck is the I value in this problem? Right? We have to think about, a solid cylinder. So we have to think about that I value. So let's take a look at what's happening here. So first, all of these forces, if you look at them, are acting perpendicular to the R value. So for this problem, for torque, we're going to use R times Ft for all of these. And our goal is to find the angular acceleration. So we're going to be looking for in this problem alpha. So if we have forces applied at a distance from a rotating axis, we have torque. And if we're looking for alpha and we have torques, we should probably use Newton's second law for rotation. So we start by saying, okay, we've got the sum of the torques, and this is really a summation, just like sum of the forces, equals I alpha. Now, how many torques do we have actually on this object? How many? We have 4 forces, agreed. Do all of those forces create torque? Yeah, which one doesn't create a torque? Think about F4. Imagine this is a handle of a door, right? You're turning a doorknob. And if you tried to turn a doorknob using F4, would it turn? It would not. Correct. And if it was a doorknob, it would resist that motion, and that would just be some sort of linear resistance. So F4 does not play a role in this problem. Okay, keep that in the back of your mind, because that's going to happen with these problems where if a force is applied, and it's applied in such a fashion that its vector, take a look, its force vector, when extended, goes through the origin or through the pivot point, it's always going to produce 0 torque. So it's not obvious right away because this vector only starts here. But if you extend the vector, you're allowed to do this. If you extend this vector, you'll see that it crosses the pivot point. And anytime a vector extended crosses a pivot point, it's exactly right. Very good. It's as if you're pushing on the door to open it at the hinge. And we did that one in class, if you guys remember. Instead of pushing on the doorknob, you push all the way over here on the hinge, and then the door, which is supposed to swing, you're pushing here, is not going to swing. No radius. Okay, so good to know. So let's keep that in mind. So we've got tau 1, and let's see. I'm going to consider, again, this is the positive direction for rotation, right? That's the counterclockwise direction there. So tau 1, as a result of F1, this force is pulling on the handle that way, which will cause this way to rotate, so that's going to be a positive. Then this force is pulling this way, which will cause it to rotate like that. That's a negative torque. This one pulling down on the right side again will cause it to rotate that way. That's another negative torque. So this is what we've got here. So the key to this problem is really recognizing when the torques are positive and negative and which torque doesn't matter, which is the torque as a result of F4. Now after this, a lot of it becomes plug and chug. So let's go through the process. Force 1 is applied at a distance capital R. So we've got F1, R1. Force 2 is applied at a distance capital R. F2, sorry, I put R1, it should just be capital R. F2 times R. And then force 3 is applied at a distance of little r. And that equals I alpha. Hey, what's I in this problem? What's I? What are we thinking? Go back to table 10.2, remember? So where are we looking at? Are we looking at a... That's okay. Are we given a length of this solid cylinder? Like a height? It is 1/2 mr squared. Let's go over that real quick. Let's discuss where that came from. And remember, r is the overall radius of the cylinder, which is big R in this problem. So let's talk about that real quick. You were not given the height of the cylinder, which in the table, I think, was that Chip? Was that you that said this, right? With the L? You're not given that length. So you have to kind of assume that the length of the cylinder is insignificant. Okay? You have to assume that the length of the cylinder is insignificant. And I want to personally, hold on, I want to really quickly look at the table as you guys are talking, because I wasn't even looking at the table there. Okay. Yeah, because I see where you're looking. I see where you're looking there, Chip. You're seeing the solid cylinder or disc about a central diameter you were looking at, I guess? Gotcha, okay. So what's interesting, though, is to notice this. I'm going to screen share real quick. Can I screen share, actually, another one? I think I can. Hold on. I could probably steal the screen share. Let's see if that works. Okay, yes, I do. Okay, so notice over here in the corner, right? This has a length to it, but the length is not included in the rotational inertia portion of the formula. So although given a length L, it's only when it's spinning about this axis that the length actually matters. So this shape here is actually what we used for the pulley. Think back on the pulley. This is really the pulley right here. A pulley is a solid cylindrical object or a disc. A pulley is a disc rotating about its central axis. So this is the pulley example. So we haven't really changed from this example, from the last example to this one, our shape, although it does look slightly different. That's my point I want to make here, that it looks different, but we're using the same general shape. I think I lost my broadcast, right? Hold on. All right, so based on what we have now, it just becomes solve for alpha. We have everything else in the problem. All these other pieces are given in the problem. So let's go ahead and divide through by the 1/2 mr squared, or double and then divide by mr squared. And let's plug in our values. So we've got 2 times that entire thing all over mr squared. And that's F1r minus F2r minus F3 little r. And that equals alpha. And now let's plug in at this point. So what do we have here? Let's see. We've got F1. I got to zoom out so I can see it better, sorry. We got F1 was given as 6. Big R is given as 12 centimeters. 12 centimeters, 12 centimeters. So big R is actually 0.12. Minus, let's see, F2 is 4 times 0.12 minus F3, which is 2 times, and that's 5 centimeters. That's going to be 0.05 meters. And then close the bracket. All over the overall mass of this big thing, which is 2 kilograms, times the big R value, which was again 0.12. That'll equal alpha. Now, here's a question for you. Could we have figured out the direction of motion from just the torques? How come?
Awesome. Well, just wanted to give you a call and just let you know that we matched you with a really great opportunity with a company called Triage Consulting. And they're
Yeah, that's an F1, yeah.
Specializes in healthcare and hospital. And so just wanted to see if this
Well, it depends on, exactly, very good. So what I'm getting at is that we don't care about the value of alpha, or if we don't need the value of alpha and we only need the direction, then all we need to do is look at the sum of the torques. If the torques going clockwise are greater than the torques going counterclockwise, then it's going to be a negative answer for the rotational direction. So remember that the torques, the net torque will tell you which way the net acceleration is acting, but it doesn't give us the value. So by dividing by the 1/2 mr squared, we're able to get the value of alpha. So what I'm pointing to is this. If I could have just calculated this right here, see where I'm circling? That right there? That's really the sum of the torques, which tells me that if this answer is negative, then this answer is negative. Just like forces. If the overall net force is negative, then the acceleration overall is negative. So think back to Newton's second law, right? If I think about F equals ma, if this is a negative quantity, m has to be positive, so a has to be negative. The same is true here. If you get a net torque equals I alpha, and the net torque turns out to be positive, well, I is always positive, so then alpha had to be positive. So what I'm getting at is that the direction of the acceleration angularly is only dictated by the sum of the torques, while the value, we have to then do the math and divide by the 1/2 mr squared here so that we can isolate alpha. Okay? What do we get for alpha in this problem? What did you guys get? I'll check my answer key to see too. I'm getting 9.7 here, it says. That's radians per second squared. And let's see, is it negative, is it positive? This gives us a positive answer, so we could say that is a counterclockwise direction. So it turned out that the 6 times the 0.12 ended up weighing, in a sense, a weighted average, or it was more valuable than these two negative torques. And why is that? Think about it. Spencer said it before, right? Yeah, 4 and 6 does give us, a 4 and 2 here does kind of balance the 6, but they don't both act at a radius of 0.12. This one acts much further in, which means its effective torque is much less. So we've got a positive value, and then we've got these two smaller negative values. When we add these up, they don't even balance out this guy, which is why we end up with a positive result. You got 1.16. I forgot to square something, I think? Yes. I got to square the MR, sorry. Down here. Right there, guys, sorry. That 0.12 should be squared in the denominator. That's me. Yeah, Chris? Okay. Sorry about that. That's me, guys. Yeah, that should be a point. That should be a squared right there. I want to end up with one last question, and I'm just going to start it so you guys can see it, and then we'll call it for today. We'll do 10.6. We'll do 10.8 in our next class to start off, and we'll carry into chapter 11. So let's end with this example just so you can see it. And this one is going to be, don't mind my pictures of me and my niece. You guys see these weird pictures looking there? Yeah. Have you seen that yet or no? Because I realize it's like the most recent picture, so whenever I use this now, because in the past when I presented, students wouldn't see what comes up here. Because I'm literally screen sharing, every time I hit this now, you can see me and my niece just making faces at each other. Yeah. Anyway, all right. So this shows, let's see, a uniform disk. So the same I value as the previous problem. It's a uniform disk. It rotates about its center like a merry-go-round. It's got a given radius. It's got a given mass. It says starting at time t equals 0, 2 of the forces are being applied tangentially to the rim so that at time equals 1.525 seconds, the disk has a velocity of 250. So here's the thing. Let's go through what's given in this problem and why it's different. So they're giving us initial time, final time, and then the angular speed. Okay, initial time, final time, angular speed. And then they give us F1's value right there. We know that the radius of the disk is given and the mass of the disk is also given. And our goal in this problem is to determine the value of F2. So we're not solving for alpha here. We need to have alpha. But we know what alpha is by definition. Alpha is the change in omega over time. And how much has omega changed? Well, omega was 0 because it said it started at time equals 0 where it's at rest. Does it say at rest? It should say at rest. Yes, initially at rest. So we know that alpha is going to be the final angular velocity minus the initial all over time. So we have an alpha value in this problem. Let's keep that in mind. We have some number for alpha right there. Actually, that'll be, right, what, 200, I guess? Yeah, it should be 200. 250 and 125 is 2, and then 2 zeros over? Yeah, okay. So there's our alpha value in this problem, and now we can do, again, sum of the torques equals I alpha, where I, again, is 1/2 mr squared, and alpha, again, is given in the problem, or solved for on the right over there. And the torques that we have are both acting perpendicular to r. So force 1, if I look at the problem, look back up here, right? Force 1 right here would cause this object to rotate clockwise, and that's going to be negative. So let's say negative torque 1. And then force 2 would cause it to rotate counterclockwise. So that'll be a positive torque 2. And then from there we just carry down our math. So negative F1 times R plus F2 times R equal 1/2 mr squared alpha. Now before you start calculating, recognize that R is going to drop off. There's going to be only one R left. So let's drop these R's off because they all happen to be the same. Do we see that? In the last problem we had little r and we had big R because the forces were applied at different radii length. But here, the moment of inertia R and the R value of the forces are applied is the exact same R, so that can drop off. So as a result, we get negative F1 plus F2 equal to 1/2 big M times alpha, and our goal is to solve for F2. Okay. Thank you, thank you. Damn, dropping things too quickly on myself. Let's see. I hate when this thing doesn't work with that, and squeeze an R in there. Yes, there's definitely an R, thanks. I think that was Matt or Chris whoever said that. Thank you. So 1/2 mr alpha plus F1 would be our result for this problem. And just so you have an idea of a number, this is number 53. Let's see. 53 turns out to be 0.14. Be careful, by the way, the units are not given in standard units in this problem, right? I think we're given grams and what else? Let's see. Yeah, grams and centimeters. So make sure to convert before you go ahead and calculate this answer. Okay, aside from that, that's kind of where I'm at today for you guys. If you want to hang around for a little bit, if you have any questions on stuff that's not clear, feel free to hang around. It's 3:40 now. It's perfect timing. So we'll start with 10.8 next class. So what I want you guys to do is over the weekend, I'm going to assign the 10.6 and 10.7 homework. Your 10.5 was already due today, and that's what I think you worked on with Alex earlier. And you could also start looking at the problem set for 10.5, and then I'll add the 10.6, 10.7 problem set. I have not assigned 10.6, 10.7 yet, but I will. And feel free to remind me with an email. I don't mind, but I'll probably be able to do it later today. Okay, if you haven't signed up for Pivot yet, you should also sign up for Pivot. And there's only 3 of you that have done it so far, so there's 7 of you that have to still do it. So please sign up, make a Pivot account. I'm I'm going to start assigning some labs to that, and the labs are going to be for rotational stuff. And then, if you recall, I also made a Shobi channel. I don't know if we're going to use that. I'm only doing it in the case that we end up having quizzes and tests, but we haven't, as a school, really addressed that yet. So as of right now, I'm not too concerned about giving you guys regular quizzes. I'd rather just be like reviewing, doing a lot of problems for the quarter. Is that clear? Okay, cool. All right. Well, let me know if you guys have any other questions. Hang around if you do. If not, I will see you all on Monday then. All right, guys. Have a good day. I don't, I said that you're welcome to drop in, put it that way. So if you want to come in and just chime in, add some comments, you can. But I told Alex and Emily the same thing as TAs. Like, right now, it's just not, there's nothing you can really do, But I did, by the way, I did something pretty cool. I did the bottle flip yesterday, the bottle flip. We did, like, the mechanics behind it. It was pretty cool. And then I'm going to do something on, like, solar energy and solar panels and stuff tomorrow. So, anyway, yeah, you're welcome to come by anytime. Tomorrow is first and second period. So if you want to just sleep in, you're welcome to sleep. Yeah. Okay. Feel free, for sure. All right, Spence. All right, you too. See you.